Good morning. Wow. Meow. Meow. Good morning. Meow. 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 Boop dee. Boop de boop. Boop de boop. Boop de boop. Oh, did you go boop de boop? Oh, you did go boop de boop, boy. What do you do? Get a boop. Oh, good boop. Good boop. Okay. We'll wait. Well, I'm going to start. Okay, good morning, everyone. So we are done talking about electric fields for now. And so now we're going to talk about something called electric potential, okay? So there is something called the electrical potential energy, okay, which is, of course, measured in joules, and it is of a charge of size Q, okay? So we have, that's electrical potential energy, and that is denoted by U of X, right? Because potential energy is a function of where you are, all right? So there's a electrical potential energy. Now, if you have, so there's another related concept called the electric potential. So this is a little bit confusing because potential, electric potential, which is the topic of today's lesson, is not the same thing as electrical potential energy. Okay? So if it doesn't say energy at the end, we're talking about this. And so the electric potential is denoted by V. All right? And it is a function of position. And it is equal to the potential energy as a function of position divided by the size of the charge. Okay? Boom. So that is the definition of electric potential. Suppose we take this equation and we take the derivative of it. All right? In fact, I'm going to do minus the derivative of it. So I'm going to do minus dV dx. So the charge, the amount of charge is just a constant. So I would have 1 over q times minus du dx. Now, if you remember, the derivative of the potential with respect to potential energy with respect to position is negative that is the same thing as the force. Okay, so this is the force, but because this was the electrical potential energy, the derivative of the electrical potential energy is the electrical force. So this is the electrical force. All right. And so this is the electrical force divided by Q. All right. Now, if you recall, the electric field is defined as the electrical force is charge times electric field. So F over Q is equal to the electric field. Okay? So this is just the electric field. So minus the derivative minus the derivative of the potential with respect to position is the electric field. Okay? So if I were to, so this is like one of our main, these two are our first two main equations for today. We're going to have three main equations. So, for example, I will just do the briefest of examples here. So let's suppose that v of x is equal to, I don't know, 7 over x squared. All right? And I wanted to know what is the force on a 2 coulomb plus 2 coulomb charge at x equals 1 meter. It's located at that position. So the first thing I would do is I would do minus the derivative of this. So minus d dx of 7 over x squared. So that's going to give us minus times minus 2 over x3. All right, so that gives us 14 over x cubed is the electric field as a function of x. Then I would plug in x equals 1, so the electric field at 1, because I want to know what is the force at 1, is going to be 14 over 1 cubed, which is just 14 newtons per coulomb. And then force is QE, so I have 2 times 14 for a force of 28 plus 28 newtons. Okay? So, ooh, it's cold. Hood back on. It's cold. So, we can actually go backwards. So it's also important to go backwards. So what if we do minus the integral of this? So what if I do minus the integral from A to B of the electric field with respect to position. Okay? So we're doing the reverse of that. Well, that would, if I do minus E, then that's going to be the integral from A to B of dv dx dx. Okay? So notice how the minus sign, all right, cancels out the minus sign here. So we have plus. And then from the, I don't know, first or second fundamental theorem of calculus, one of those fundamental theorems of calculus, this is equal to VB minus VA. So the potential difference is related to the integral of the electric field. So this is our third important equation. Now, it is not part of the AP Physics C or the IB curriculum to teach this, but I just wanted to talk really briefly about, because I think it's cool. How does this work in 3 dimensions? Okay, so what if I had a potential that is a function of x, y, and z? So it's a function because, you know, the real world is 3-dimensional. Okay, so the electric potential is also depends on 3 variables. That could actually depend on 4. It can depend on time as well. So so in that case, let me just give an example. Let's say it's a constant times x times y squared times z to the 5th. Okay? So if I wanted the x component of the electric field, I would do minus the derivative with respect to x, but I'm going to treat y and z like they're constants. So all these are constants, and I'm just taking the derivative of x, which is 1. Okay? So I would have minus c y squared times z to the 5th. So the x component of the electric field depends on where you are. All right? It depends on both your y coordinate and your z coordinate. If I wanted the y component of the electric field, I take the derivative with respect to y, treating z like it's a constant. Okay? So I would take the derivative of my potential. So I'm only focusing on the part that depends on y. So the derivative of y squared is 2y. All right, and I leave everything else the same. So I get minus 2c xy. So here's the 2y, z to the 5th. All right, so the y component of the electric field depends on both x, y, and z. And then the z component.
Don't do that, Ivan.
Ivan has asthma, and so, he has like allergies or asthma or something, so he'll be like, and he's like wheezing, and he was wheezing all day yesterday, so I'm not letting him outside today, and he is pissed off. He is really frustrated by that, because he expects to go outside every single day. That's his routine. So to get the z component of the electric fields, I'm going to take the derivative with respect to z. So I'm going to treat x and y like they're constants and only take the derivative of that part. Okay, so that's 5z to the 4th. So I would get minus 5cxy squared z to the 4th. Okay, So this kind of operation where we take the derivative with respect to one variable, but we treat the other variables like constants, is what's called a partial derivative. Okay, and it has a special symbol. So I didn't use that special symbol here, but I will show you what the special symbol is. So the x component of the electric field is minus dv dx. So you use, it's a d, but it's like a curly d. All right. Almost like an upside down e. All right. So that's the symbol for partial derivative. So whenever you see that, it means treat any other variables in there like they're a constant except for x. And then the y component is the partial derivative with respect to y. And the z component is negative the partial derivative with respect to z. All right. So that is how that that works in 3 dimensions, which I think is kind of neat. It's such an easy generalization that I just wanted to talk about it. Okay. Let's talk about the units of let's talk about the units of electric potential. Okay. And so the units of electric potential are going to be, let's see, well, electric potential is defined as potential energy divided by charge. So what that means is that the units of electric potential, all right, are equal to the units of potential energy divided by the units of charge. So that means, so the units of potential energy are joules, the units of charge are coulombs. So electric potential is measured in joules per coulomb, but that has a special name. It is called the volt, which is abbreviated V. All right, so the volt V are the units of electric potential. That can be a little bit confusing because, you know, you could have an equation like saying that the electric potential at 2 meters is equal to 7V. So it kind of like, you know, it's pretty confusing. It's almost like you want to cancel those out. But by context, you should know whether this V is representing the function, the potential function, or the variable volt. Okay. If I really think it's going to be confusing, I might use an alternative definition or an alternative symbol, which is the Greek letter phi. So I might say phi of x is u over q sometimes. Okay. So what I've observed is that in America, textbooks that are written by American authors tend to have V of x, and if it's a Russian author of the textbook, they tend to use phi of x. So different countries have different symbols for what they prefer to use. Okay, so yeah. So let's talk about the potential due to a single charge. Okay. So there's a nice and easy formula. It says that the potential due to a single charge is KQ over R. All right. So charges create potential. So R is the distance from the charge. Okay. So the further you measure the potential away from the charge, the smaller the potential will be, or the closer to zero it will be. Okay. So notice how this is 1 over R. It's very close to electric field, except it's, and we can double check why this is true, right? Because if we do minus dV dr, we would get KQ over R squared, which is the electric field due to a single charge. All right, so that's why that is the formula. It's because if we do negative the derivative, we get the electric field, which is the exact relationship we talked about right here. All right, so this is the electric potential due to a single charge. And that is our last important formula for today. Okay. Q can be positive or negative. All right. So let's suppose that we wanted the total potential. All right. So the total potential at a position X, all right, is going to be equal to the sum of the potentials at X due to the individual charges. Okay, so to see how this works, we're going to do a couple of examples. Okay. All right. So the first example is, let's suppose we have two positive charges. So this one is plus Q1, and it is at X equals 0. All right. And then this is plus Q2, and it is at X equals L. All right. And we want to know what is the potential right here at some location X in between them. All right. So the potential at X is going to be the sum of two terms. There's going to be KQ1 over R plus KQ2 over R. All right. So let's figure out what are these distances. Well, the distance from here to here between 0 and X is just X. So this distance right here is X. This distance right here is the rest of the distance to X equals L. So that's going to be L minus X. All right. So that would be the potential at a random location. And then if I wanted the electric field, I would take the derivative. Okay, so the electric field at X is going to be KQ over X squared minus KQ2 over L minus X quantity squared. All right. So that's how that works. It's pretty simple. So you can do things like, You can do things like have squares of charges. You can have triangles of charges. All the same stuff we did with electric fields. Okay. But let me tell you an incredibly important point. The electric potential is a scalar. Okay? Meaning it has no direction. So if we thought about doing electric fields, we had to worry about the directions because the electric field is a vector. So, for example, if two electric fields point in opposite directions, they cancel each other out. Okay? If two vectors are at angles to each other like this, then when we add them, we have to do the parallelogram rule to add them together. But you don't have to do that for vectors, or I mean for electric potentials, because they're just scalars. So you just add them up like scalars. Okay? You don't need to add them up like vectors worrying about directions. Okay? So because of this, you don't have to worry about direction. When adding. So this means that it is oftentimes easier to work with electric potential. Okay? So, in more advanced physics classes, you pretty much work entirely with the electric potential. Okay? And then, once you're done with your calculation for the electric potential, you follow this rule and you generate the components of the electric field afterwards. Okay? Because if we were to start out by trying to calculate the electric field, then we have to worry about the ij and k components of the electric field and whether they're canceling out or adding together or whatever, and it gets more complicated. Let me show you how that works. What if we had a dipole? Okay, so we have here is x equals 0, and here is a charge minus q is at the origin. Okay, and then here at x equals d is a plus q charge. So this is called a dipole. We have two charges that are equal and opposite, and they're separated by some distance. Okay. So here's the y-axis, and here's the x-axis. And what if we have a point P right here? Okay. And it is at coordinates x comma y. And we want to know what is the potential at x comma y. All right. So what we have to do is we have to figure out what are these distances. So this is the distance from minus q to the point P. And I can see from the Pythagorean theorem that that's going to be square root of x squared plus y squared. All right. So the potential at point P due to this charge is going to be k times minus q over square root of x squared plus y squared. All right. Then we have to find out this distance. Okay. Now, if we look at this point as x, so this distance, we have the same y coordinate, but this distance for this right triangle here is less. This is x minus d. So that means that this distance is square root of x minus d squared plus y squared. Okay, so then we have the potential due to this charge, which is a plus Q charge, and it's going to be K times plus Q over square root of X minus D quantity squared plus Y squared. All right, so that is the potential due to a dipole. Now we could go on and we could get the X component of the electric field. That would be minus the derivative, the partial derivative with respect to X. We could get the Y component of the electric field. All right, which would be the partial derivative with respect to Y. And then we could get the total electric field due to the dipole, which is going to be a function of X and Y, and it's going to be just that. Okay, so I'm not going to do that calculation. The thing I'm most interested in is this part, because we're talking about potential today, and I'm not requiring you to do partial derivatives. But that's how it works. All right. So the quiz for today, it has two parts. The first part is going to be playing around with this formula and that formula. And then the second part is going to be calculating the electric potential at different locations using this formula. Okay, so this is the electric potential due to a discrete charge distribution. So that was my lesson for today, and I'll see you in the Zoom room. Bye-bye.